So we're up to our third part in this little mini series about system pressure transmitters. Definitely want to try and wrap this one up. This is just dragging on for way too long. In the first video we spoke about where should we install the pressure transmitter. The second video was, I think we did 3 points to consider, and in this video 2 more points to consider when selecting the best location for your system pressure transmitter. Now, the first thing we're going to talk about is a manifold. All system pressure transmitters, in my opinion, should be provided with a manifold, which is basically an arrangement of 3 little mechanical or manual isolation valves that are provided by the mechanical contractor. Sometimes they are individual little valves, an isolation valve for the supply, an isolation valve for the return, and a bypass little isolation valve. But sometimes you can purchase them pre-arranged on a little plate. There's a supply isolation, the return isolation, and a little bypass on a little plate that you just install and connect everything up to. So if we have our pressure transmitter, this is our chilled water system pressure transmitter, or it's the pressure transmitter across each of the chiller's evaporator. There's the plus port and the minus port. And if we have this is our chilled water main pipe runs, the flow and the return, or the supply and the return. These are the main pipes we want to measure the pressure across. So usually mechanical will weld onto this pipe a socket. So usually when mechanical does this, and they've got this sort of 6mm copper tube that runs from the pressure transmitter to the pipe, where they've got the socket sort of welded into the pipe, they will usually provide a little isolation valve, 2 little manual isolation valves that originally they're sort of closed off, and then they'll weld this in and they'll put the pipe in here, and then they fill the water up into the circuit. They will then open these little valves, and it will put pressure onto the transmitter. And obviously if the transmitter fails or there's an issue, you can isolate this and the water is sort of isolated. You can remove this and replace it. So I think in any country, we will almost always have these 2 little mini isolation valves. Now there's supposed to be a third one called the bypass valve. And this might be the little valve that doesn't exist on every single job. Sometimes I see that these aren't here. In Australia, we do normally have these because it's quite well known in the industry, but not everyone knows why it's there or how to do it. So in this part of the video, I'm going to explain to you why we have this third bypass valve and why it's incredibly important. So the problem we have, actually before we get to the problem, let me explain this. In my opinion, most pressure sensors work with a diaphragm. So inside here, there's a diaphragm. I'm not saying they all do this. I think they mostly do. There's probably other types of sensing arrangement, but the ones that I think we have the most of is this diaphragm method. And what happens is, say this transmitter is sitting in the basement and you've got 30 floors of commercial office above you. There's a lot of static pressure in that pipe. The static head that's in this pipe, all the water that sits in this pipe, there's a pressure that sits on the flow and return on the whole building. So that pressure sits in here. So say for example, you've got 250 kPa of pressure sitting in here. And then when the system is completely turned off and there's no pumps running, there might be another 250 kPa sitting here. So there's 250 kPa here, there's 250 kPa here. This is the head, the static head in the 30, 40, 50 story commercial office sitting on here. So because on the plus there's 250 and this negative there's 250, there's 250 pushing this way and there's 250 pushing this way. The diaphragm is sitting sort of balanced, and the difference, the differential pressure transmitter, it's called a differential pressure transmitter because it's the difference between the plus and the minus, is 0 kPa. And then when you start the pump in the flow, this pressure increases. So let's say there's a difference then. Let's say the pump's running. So the difference between the flow and the return pipe, or the pressure, is 250. And that's how the differential pressure transmitter works. What's very important to understand here is that, in my opinion, the diaphragm can withstand a reasonable amount of pressure as long as that pressure is equal on both sides. It's equally pressing on the diaphragm, the same amount of pressure. This diaphragm cannot withstand a lot of pressure on one side, but not the other side, because the pressure just bursts the diaphragm out. So if we had, this 250 kPa of head across the whole building, and let's say this was closed, so we've got the static head of the building through this open mini isolation valve. If this is closed, if that 250 comes through here and sits on here and presses on the diaphragm, and this is closed, there's nothing here, it'll burst the diaphragm, the sensor will fail and need to be replaced. So that's why we have this bypass valve in the middle here. So usually when we start, they're all closed. So the mechanical pipe fitter will come along, he'll install these 3 valves, he'll weld this in, connect it all up, and they're normally closed when you start. They're all closed. And then what happens is that the mechanical pipe fitter, they want to test that there's no leakage points in this connection, the connection on these valves, and this connection here. So the mechanical pipe fitter will open this valve first. The water pressure will come through here. This is closed. It comes to here. That full static pressure comes through here, bursts the diaphragm. He checks there's no leaks. Then he opens this valve and the water pressure comes through. He checks there's no leaks. I've had it before where when the chillers are in the basement and there's a large head above, I've had it that every single pressure transmitter across the 3 chillers evaporator, the mechanical pipe fitter, bursts the diaphragm when he does the leak test. It doesn't matter which one you open. If this is closed and you open this one first, all the pressure comes through, closed, it all comes into here, it bursts the diaphragm. I used to get so frustrated with this that I'd almost sarcastically be saying to my colleagues, you know what, I'm going to buy 2 pressure transmitters for all the chillers on every job because the mechanical guy bursts the diaphragm every single time. That's why this valve is here. What you're supposed to do is this. The mechanical person should first open the bypass first. And then when they open this one through the leak test, the pressure comes through here. Because this is open, it comes through both of them. And it applies this pressure equally to both ports. The diaphragm does not burst. Then he opens this one to check for leaks in this pipe and this connection over here. The pressure comes through, stabilizes through the bypass. The pressure is the same. Then you close this. So the sequence is open this first, open these 2 however you want in any sequence. Once the pressure across the diaphragm is balanced, then you close this again. That's very important. If you're a service technician and you replace this pressure transmitter and you don't understand how you do these 3 valves, you could burst a brand new one straight away again. So in this part of the video, I'm talking about, the first thing we got to do is you should have this manifold. Now, sometimes this is installed as 3 individual valves. They might put them here maybe. They might put them there sometimes. But you can also get a little plate made up. And I call this a manifold. I don't know if it's the right name. But a little plate made up. So Mechanical makes a plate. They install these 3 tiny little valves, manual valves in their factory, and then they install this thing next to the transmitter. He's got to make this pipework connection here and these 2 pipework connections here. I call this a manifold. I'm not sure if it's the right name to call it. So the first thing here, the first takeaway here is, if you're a BMS person, you need to be aware of this. Otherwise, you're going to have burst transmitters. Now, if your chillers are installed on the roof of the building, it's not such an issue because on the roof of the building, there isn't this massive static pressure head that's sitting in there. So on the roof of the building, you might not actually need this. But I think for consistency, we should have a manifold arrangement for every single water pressure transmitter throughout the project. System pressure transmitters and the pressure transmitter across each chiller's evaporator. This is an important thing. I've had lots of these things fail because of this. The second thing that we need to do is, I like to sort of consider this health and safety. Now, I used to be a service technician a long time ago. So when I do BMS design, I think about what the service technician has to do and how they're going to maintain this transmitter for the next 20 years. Even though you might upgrade this transmitter, after 5 or 10 or 15 or 20 years, the actual installation arrangement won't actually change. So let's think about this a little bit further. Let's say you've looked at the schematic. So here's your chill water schematic. Here's our chilled water schematic, and there's pipes everywhere. There's something over here, and there's a thing over here, and there's a plant room here. And you determine that on the chilled water schematic, this is the best location for the mechanical fitter to weld in these sockets. That's where you want it. That's a good representation of the load. You need to get the layout drawings that shows the pipework runs, or go to site and have a look at this. Because what can easily happen is, let's say for example, you go to site and, let's say you're walking through the plant room. Here's a wall. Here's the roof of the plant room. And there's a door over here. There's a door, and it goes from the chiller plant room to the AHU plant room. And the pipes are running along here. Here's the flow pipe. Here's the return pipe. They're running down the plant room, out of this plant room. They're going through this wall. And if in your schematic, that location there happens to be right over here, then what will happen is the mechanical pipe fitter will weld that socket on over this socket here, these two sockets. They'll get welded onto here. And what happens is your BMS installer is going to come here. They might install the transmitter up here on the wall. It's a good location. There's a bit of a wall there. They can screw on the plate, maybe the manifold, with the 3 valves. Maybe it goes there, so that goes into the manifold like that. Cable comes along here. Bit of a containment route along here. Here's the cable. It's a great location from the point of view of good control, but it's above a door here. So the service technician has to get the ladder there and get up to service this pressure transmitter for the next 20 years. Replace it, fix it, check if there's leakages, try and drain the air out of this pipe. This is quite a high location. It's above the pipe maybe, so you can get air in here. So maybe they've got to try and bleed the air out, maybe, sort of thing. And then someone opens the door, knocks the ladder over, and there's your buddy lying on the floor with a sore head. So this is a situation where we very easily end up with a sensor in a good location for control, but health and safety wise, it's a very bad location. Another thing that can happen is, let's say, here's the wall again in the plant room, and it's like a side view. Here's the flow pipe. Here's the return pipe. And on your schematic, this was a good location, and that good location, maybe it's over here. So, mechanical welds the socket in here. That's all they pretty much do. And then your installer comes along, and again, he puts the transmitter on the wall over here. It's a good it's sort of like this, I guess. Here's the transmitter installed on the wall. It's a good location. But again, the service technician needs to come here with a ladder, get up the ladder. So we're working at heights unnecessarily. So what we want is the transmitter to be installed here. 1.5 meters, or maybe 2 meters above ground at eye level. Now, mechanical will run the 6mm copper tubes down to here. If you told them to do that, in your design phase, you told them, I need the manifold here with the 3 valves on, and I need this installed at a safe working height, 1.5 meters, they would probably do that. But if you don't tell them that, they won't do it. So I think in last week's video, we spoke about this idea about having this installation little check sheet or cheat sheet or little specification that you would issue to your electrical subcontractor that explains all the requirements for your company's rules around installation. You could create the exact same little sheet to give the mechanical contractors for the installation of the system pressure transmitter, how that works. So maybe you would draw this on this little check sheet for mechanical. Maybe you would say here on the sheet, it should be installed at 1.5 meters to 2 meters above finished floor level. Maybe you tell them that on the sheet. Maybe you tell them that, this pipe needs to be 6mm copper. You tell them that. You tell them that you need a manifold with 2 times little isolation valves and 1 times bypass valve. You tell them that in the sheet. I think in the UK and here in Australia, this is a 1/2 inch British standard pipe. I think it is. I can't remember. 1/2 inch British standard pipe fitting. In America, I think you use, is it NPT? National Pipe Thread, maybe? Don't know what that would be. So in the sheet you say that because this sensor could come from the US and it might have an NPT thread on this, but you need British Standard Pipe thread here in the UK or in other Commonwealth countries. I'm not sure about what Europe does. So you might need to buy a little fit. So if you have a little sheet that you issue to mechanical, it tells them that. And then you could probably have some rules around what does that mean? Like you say, you got to tell them that the transmitter needs to always be installed, at a safe working height. So they know they're going to do that. If you don't tell them that, it doesn't happen. So there was two things there. It was the manifold. I think it's very important. Do you have one? Yes or no? And if you do have them, do you understand how the middle bypass valve works? It's very important. It's very important that we educate the mechanical contractor also, and their plumbers, how that works so they don't keep bursting our pressure transmitters. The second part was health and safety. Everyone talks about health and safety, but very few people actually act on it. It's very important. It's very important to, when you're doing your design, to think, okay, I'm the service technician. How am I going to service this equipment safely for a very long time? And I guess that also flows into the second part of that, where once you've done your theoretical design, you've looked at the schematic, you've sized the correct pressure transmitter, it's a 0 to 250 kPa transmitter, the cabling, there's all that sort of stuff, the points lists, you've done all the hard work. Stop and then cross-check that against the physical on-site constraints. Look at the pipework layout drawings, go to site, have a look at what it looks like. Oh, that's not actually a great spot. You might have on the schematic that this is a good spot to install a transmitter, but there's nothing there. It's in the middle of the plant room. There's no wall there. There's no concrete column there. What are they going to fit? How is your installation contractor, where they're going to install the transmitter? There's nothing there. It's in the middle of nowhere. You can't put it on the ceiling, I don't think. So go there and check those sort of things. I would regularly walk into a boiler plant room. There's two big boilers. The flow pipes come out, and there's two temperature sensors up there above the boilers. It's not a great location. You've got to lean the ladder up against the boiler to get the sensor. Put the sensors 4 meters further down in a nice open space, get the ladder up. Obviously a temperature sensor just goes into the pipe. You don't need to install the transmitter remote. It's easier than the pressure transmitter. The best location for control is not necessarily the best location for practical reasons. Have some respect for our service technicians. We don't think about the service techs enough in design. You're working here for a year or two on this project. They've got to live with the location of the sensors for a very long time. I'll tell you another interesting thing that happened last year. It was a shopping center, and they did a chill water system upgrade, new chillers and pumps. The whole plant room was upgraded, and we retained the original system pressure transmitter, which was far away into the shopping center in a good location. And we just had really bad control, and I had to go back to site to try and determine why this wasn't working. Met the BMS company there. We were looking at the graphics, and the graphics said there that the system pressure set point for pump control was 200 kPa. And I was thinking that's a long way away. The pressure normally down there is 100 kPa. It's not 200. It doesn't make sense. So I phoned up the mechanical contractor. Hey, when you guys did the water balancing, did you give the BMS company the design pressure set point? He said, yep, it was 200 kPa, yep. I said to them on the phone, where did you take that pressure reading? And he said, in the plant room. What happened was that weekend when they're doing the water balancing for the design conditions, the BMS guys weren't there, I guess, and they just took the pressure reading in the plant room. As the pipes left the plant room to go out to the shopping center, they took a pressure reading in the plant room, quite close to the pumps, 200 kPa. The transmitter was down there. So we had to go back and open all the chiller valves back up again, pull the pumps into design speed, get everything balanced again, and then take a pressure reading where the transmitter is. So you as the BMS engineer, you've got to coordinate with mechanical to make sure that after balancing, they go and read the pressures in the locations where your transmitters are. If they're rushing to finish and you haven't coordinated that, they'll take a pressure reading somewhere else. So here's a great example of, it's a great successful project, but the pressure set point that you, the BMS company, are controlling to is not where your transmitter is. It's been an example. All right, guys, we've obviously covered a lot of information in the last 3 videos. And, go back, watch them again, write down some notes. I think I was complaining about this the other day. But remember this. It's not just about your personal growth and development, these videos, right? As you're learning these things, feed them back into your company. So as we said before, the electrical installation for your company, the check sheet. Now we have, a 1-pager for the mechanical installers that tells them about the pressure transmitters, copper, the manifold, eye level. We've got that sheet now. So work with your company to do these things. It completely freaks me out that every generation that comes into the industry starts like fresh and makes the exact same mistakes. So it's taken me 20 years of mistakes to get to where I am now. And I find it particularly frustrating because in my role, I deal with BMS companies all the time, witnessing, reviewing their designs, signing off, whatever it is. So I'm watching them there all the time, and I see young engineers come into the industry, and then I watch them, I review their designs, I do witnessing, they make the exact same mistakes, they get better and better and better and better and better. Then the next batch, the next generation comes in, they make the exact same mistakes. Like, how is it that we enter into our industry, you're a young engineer, and you've got to bugger up the first few jobs until you learn from trial and error? That's not acceptable. We need to try and learn these things, not just for your own personal development. Talk to your manager, create little working groups at your BMS company. Let's say you and two others are going to work on this thing. Maybe another one of you is going to work on a side project, a mini project around energy management systems and virtual meters and visualization and COP and that, and then have somebody else work on something else. Create little working groups in your company and start documenting the changes. The best way to do that is a thing called lessons learned. Like, you read any project management book, there's 2 of them there. I think I've showed you before in videos, or was it a training course? I can't remember. Every project management book you read talks about lessons learned. At the end of the project, there's lessons learned. So talk to your boss, or if you are the boss, create a process that at the end of every single project, the lead engineer has to present lessons learned to the team. So once a month, the last Friday of the month, whatever it is, you guys have a team meeting, your toolbox talks, I don't know what you call in other countries, or virtual meetings. Every month, let's schedule it that some engineer has to present the lessons learned. On this job, these are the things that went well, these are the things that went poorly, and then put together a plan that you and your colleagues and your boss will take those lessons learned and feed them into a process that you document so that you have a repeatable quality of delivery. Every company has an A team and a B team. Why is that? That's because the A team has just been there for longer and stuffed up more jobs and learned their lessons. The B team is still going through their learning curve. How do we do that? How is that acceptable? So start feeding back into a process that we follow on every single job. This is the process. The company I work for has a process. It ensures the quality of what we do so that when mechanical contractors are going out to tender to select BMS companies, this company, ABC, we've worked with them 5 times. Their design, installation, engineering, commissioning, their process is exactly the same. It's not dependent on what technician is working the job. The company, the brand of the business. That's what's important.